Hi, I am Prathame. Welcome you all to another episode of the 24th Universe. In this video, we shall see what are number systems and how to convert them to other number systems in an easy way. So first things first, what is a number system? A number system or a numeral system is a writing system for expressing numbers, that is, a mathematical notation for representing numbers of a given set using digits or other symbols in a consistent manner. Here are some examples. All these numbers uses a base 10 system, but the notations used are different. The same sequence of symbols may represent different numbers in different number systems. For example, the notation 11 represents the number 11 in decimal number system, but the same notation 11 represents the number 3 in binary number system and the number 2 in unary number system. Let us now see in brief few of the different number systems. Unary number system. The unary number system, for example, telemarks, is the simplest number system which is used even today. To represent a number n, a symbol representing 1 is repeated n times. To count things, you just have to put that many marks. This method is easy but not efficient. Decimal number system. The decimal number system is also called the base 10 positional number system. This number system is most common system used globally, that is, which you and I understand. It uses a different symbol to represent different amount of things with the numbers 0 to 9. Each symbol indicates a different amount of things. If we want to represent something that is higher than 9, then we write a digit to the left and make the first digit back to 0 and start over again. Since it increases the amount of things we can represent exponentially, this system is efficient. In this system, we add digit to left every 10 symbols. Each digit represents an increasing power of 10. Example 42537. We have here 7 ones, 3 tens, 5 hundreds, 2 thousands, 4 ten thousands, and we read it as 42,537. Binary number system. Binary number system is same like decimal number system, but instead of digit going from 0 to 9, it goes from 0 to 1. Counting upwards sounds like 0, 1, 10, 11, 100, 101, 110, 111, 1000, and so on. Since each digit of binary has only two values, each additional digit represents an increasing power of 2. Example 10101. We have here 1 ones, 0 twos, 1 fours, 0 eights, 1 sixteens. This method is not efficient as decimal number system but exponentially more efficient than telemarks. Octal number system. In octal number system, the digit goes from 0 to 7. Counting upwards in octal would sound like 0, 1, 2, 3, 4, 5, 6, 7, 10, 11, 12, 13, 14, 15, 16, 17, 20, and so on. Here, each digit of octal has 8 values, so each additional digit represents an increasing power of 8. Example 7653. We have here 3 ones, 5 eights, 6 64s, and 7 512s. Hexadecimal number system. In hexadecimal number system, the digit goes from 0 to F, that is 0 to 9, and then from A to F, which represents 10 to 15. Counting upwards in hexadecimal sounds like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 1A, 1B, 1C, 1D, 1E, 1F, and so on. Since in this system, each digit of hexadecimal number has 16 values, Each additional digit represents an increasing power of 16. Example, in 453, we have 3 ones, 5 sixteens and 4 256s. There are other number systems such as duodecimal number system, also known as base 12 or dozenal number system, is a positional number system using 12 at its base. Here, the digit goes from 0 to 9 and then x and e. Counting upwards in duodecimal sounds like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, x, e, 10, 11, 12, 13, 14, 15, and so on. Here, each additional digit represents an increasing power of 12. Example, 453. We have here 3 ones, 5 12s, and 4 144s. This is more efficient than decimal number system because base 12 has more factors than base 10. Another system is the sexagesimal system. It was an ancient system of counting, calculation, and numerical notation with 60 at its base. Sexagesimal system is also known as base 60. It originated with the ancient Sumerians in the 3rd millennium BC, was passed down to the ancient Babylonians, and is still used in a modified form for measuring time, angles, and geographic coordinates. Here is an example of Sumerian sexagesimal place value number system. In computer science, we use 4 types of number systems: binary number system, octal number system, decimal number system, and hexadecimal number system. Now the question is, what is the need to convert into different number systems? This question needs a separate video altogether, but for now, let me answer it in brief. Computers use the binary system, base 2, which is easier to express in hexadecimal, base 16, taking 4 bits at a time. Because we are familiar with the decimal system, it is necessary to program computers to convert from the hexadecimal system back to the decimal system. So with 4 types, there are 12 conversions possible. They are binary to decimal, binary to octal, binary to hexadecimal, decimal to binary, decimal to octal, decimal to hexadecimal, octal to binary, octal to decimal, octal to hexadecimal, and hexadecimal to binary, hexadecimal to octal, and hexadecimal to decimal. Just look at this chart. This is how you actually convert them, but it is long and difficult method. Take a screenshot of this so that you can refer it later. You do have an easy way to convert which will reduce the conversions to only 6 conversions. You can take the screenshot of this too. You just have to remember the conversions between binary to other base systems and vice versa. And this will make the conversions really easy. Now, let's look at these conversions one by one. The first conversion is binary to decimal. Here, we multiply every digit in the binary number with its base raised to the power based on its position. This is done by starting from the rightmost digit and moving on to the left and summing up all the values. Easy trick here is to memorize the 2's powers. As you practice, you will automatically memorize it. Let us understand that with an example. We have 1001011. First, write down the binary number and above them list the powers of 2 from right to left. Expand the powers. Once you memorize the 2's power, you just have to write them 1, 2, 4, 8, 16, 32, 64. Connect the digits in the binary number with their corresponding powers of 2. Write down the final value of each power of 2. That is, 1 times 1 is 1, 2 times 1 is 2, 4 times 0 is 0, 8 times 1 is 8, 16 times 0 is 0, 32 times 0 is 0 and 64 times 1 is 64. Sum it up and you get 75 as the decimal number. And use this method to convert a binary number with a decimal point to a decimal number. The next type of conversion is binary to octal. Arrange the digits into group of 3 bits starting from the rightmost digit. A leading 0 can be added to make group. Then convert each group into corresponding octal equivalent using binary to decimal conversion. Let us understand this with an example. Group all the ones and zeros in the binary number in sets of 3 starting from the far right. Add zeros to the left of the last digit if you don't have enough digits to make a set of 3. Convert each 3-digit group binary number to decimal number separately. That is, write 2's powers for each group separately. Write the decimal value starting from the rightmost digit. 1 times 1 is 1, 2 times 0 is 0, 4 times 0 is 0. Next group, 1 times 1 is 1, 2 times 1 is 2, 4 times 0 is 0. Next group, 1 times 1 is 1, 2 times 0 is 0, 4 times 0 is 0. So, in each group, you have these decimal values. Add the numbers in each group. Now you have 1, 3 and 1. Put them together to get the final octal number, that is 131. Next conversion is binary to hexadecimal. Here, in order to convert, we have to arrange the digits into group of 4 bits, starting from the rightmost digit. A leading 0 can be added to make group. Then convert each group into corresponding hexadecimal equivalent using binary to decimal conversion. Let us understand this with an example. 1110001 is a binary number. Group all the ones and zeros in the binary number in sets of 4, starting from the far right. Add zeros to the left of the last digit if you don't have enough digits to make a set of 4. Convert each 4-digit group binary number to decimal number separately. That is, writing the expanded 2's powers for each group separately. Write the number decimal value starting from the rightmost digit. 1 times 1 is 1, 2 times 0 is 0, 4 times 0 is 0, 8 times 0 is 0. Next group, 1 times 1 is 1, 2 times 1 is 2, 4 times 1 is 4 and 8 times 0 is 0. So, in each group you have these decimal values. Add these numbers in each group. Now you have 7 and 1. Put them together to get the final hexadecimal number, that is 71. Decimal to binary. Here we divide the given decimal number by 2, where it gives a result along with the remainder. Place the remainders in such a way that required binary number will be obtained. Let us do that with an example. 765 is a decimal number. Divide the number by 2, writing the quotient and the remainder like this. Divide until you reach 0. The remainder starting from the digit from the bottom to the upwards is the binary number 1010111101. Octal to binary. Easy method is separate each digit of octal number and divide each digit by 2 to get binary number of 3 digits and group them back to get the required binary number. Consider an example 762. Here, every digit of octal is converted to binary equivalent like this. Now, collect the remainder starting the digit from the bottom to the upwards in each group. Add leading zeros to each group if it is not a group of 3 bits. Now, join them together to get the required binary number 1111100001. Hexadecimal to binary. Easy method is separate each digit of hexadecimal number and divide each digit by 2 to get binary number of 4 digits and group them back to get the required binary number. Consider the same example 762. Here, every digit of hexadecimal is converted to binary equivalent like this. Now, collect the remainder starting the digit from the bottom to the upwards in each group. Add leading zeros to each group if it is not a group of 4 bits. Now join them together to get the required binary number 0 1 1 1 0 1 1 0 0 0 0 1. Decimal to octal. Just convert decimal to binary and then convert binary to octal. Here is an example. A decimal number 87 is first converted to binary number 1010111, which is then converted to octal number 127. Decimal to hexadecimal. Just convert decimal to binary and then convert binary to hexadecimal. Here is an example. The same decimal number 87 is converted to binary number 1010111 and then to a hexadecimal number 57. Octal to decimal. Just convert octal to binary and then binary to decimal. For example, the octal number 76 is converted first to binary number 111110 and then to a decimal number 62. Octal to hexadecimal. Easy method is to convert from octal to binary and then from binary to hexadecimal. For example, the octal number 76 is converted first to binary number 111110 and then to a hexadecimal number 3e. Hexadecimal to octal. Just convert from hexadecimal to binary and then from binary to octal number. For example, the hexadecimal number 76 is first converted to binary number 011101110 and then to an octal number 166. Hexadecimal to decimal. Just convert hexadecimal to binary and then binary to decimal. For example, the hexadecimal number 76 is first converted to binary number 011101110 and then to a decimal number 118. That's all for now. I would highly appreciate if you comment here as feedback so that I can do improvements. Additionally, if you like my videos, then please leave a thumbs up. That would encourage me to do more such videos. Many thanks for watching. See you soon in my next video.